Hello, good evening. Are you able to see the screen? Can someone confirm if they are able to see the slide?
Yes.
Okay. We'll start the class in, I think, in 1 or 2 minutes. I'm waiting for a few more people to join. Okay. So, okay, so let me start now. So, welcome everyone to the NPTEL online course on water and wastewater treatment. So, we are going to uh, start with the problem solving and doubt clarification session for week 2. So as you all know, the course instructor for this course is Dr. Bhanu Prakash from IIT Roorkee, and I am one of the teaching assistant. My name is Akash Saha, and I am a PMRF scholar at the Department of Civil Engineering at IIT Madras, where I am pursuing my PhD in environmental engineering. So apologies for not taking the class last Tuesday because I was not feeling well, so I couldn't take the class. So that's why we have scheduled it on today on Friday, but all our future classes will be taken on Tuesday. So every Tuesday from 7 to 9 p.m. we'll be having the class. If at all there is any changes, you will be intimated. I hope the NPTEL team have already told you about this. So uh, not to worry about it. We will definitely take the class, if not on that particular day, but on a day later. Okay, so coming to the week 2 lecture. So last week we discussed something about various type of reactors. So today we are going to dig deeper into that, and we are going to look into the mass balance of various type of reactors like the batch reactor, CSTR, PFAR. I just gave a brief introduction, but you might have gone through the lectures in this week. So this week was all about these reactors. Okay, and then the water quality parameters are also discussed in this week's lecture. We started with BOD, COD, and then dissolved oxygen. What are the different ways to measure them, and what are the different nutrients in water? So this was all about the content of week 2 lectures. I hope you have gone through the lectures, and now we'll be solving some problems. And while solving these problems, we'll be also revising some of these concepts. Okay, and if you have any doubt, you can stop me anywhere at any point of time, and then we can take this up. Okay, so let us start with the first question. So it says that in a CSTR, that is a continuous stirred type reactor, which assumption is made about the concentration in the reactor? Okay, so does it varies with distance in the reactor, or it is constant and equal to the influent concentration, or it is constant and equal to the effluent concentration? So we are talking about a CSTR here. So what do you think is the correct assumption regarding the concentration in the reactor? Okay, so you can type,
See,
yeah. So you can, others also can type the answer in the chat box. Uh, it will be easier for you. So once I get some answers, we will discuss like how and what are the other assumptions also we will discuss. So some people are answering it as C. Any other answer? Any other answer from anyone? Option B. Okay, yeah. Okay, so I think most of you are answering it as correctly. It is option C only. So the concentration in the reactor is constant and it is always equal to the effluent concentration. Okay, so let us see what are the assumptions in a CSTR. So the first assumption is there should be a perfect mixing. Okay, so the content of the reactors are assumed to be perfectly mixed. Okay, meaning that the reactants and the product is uniform throughout the reactor at any given time. Okay, so there should be perfect mixing. Next, the outlet concentration is equal to the reactor concentration. So this is the assumption which we saw in the question. Then there should be a steady state operation. Okay, so unless and until it is mentioned, okay, specifically mentioned, we always assume that the CSTR is operating at a steady state. By the meaning of steady state, it says that the concentration will not change with respect to time. So that's why dc by dt, that is the change in concentration with respect to the change in time, is always zero. Okay, so the in steady state operation, always remember the concentration with respect to time doesn't change. Next, constant density. Okay, so for liquid, it is assumed that the density should be constant. Okay, so it basically simplifies the mass balance. So when we do the mass balance, you will come to know. So if the density is also changing, then it is difficult to calculate. Okay, so higher order mathematics will be required, but we assume that the density is also constant, and also there is an instantaneous mixing. So we know in the CSTR there is an influent concentration coming in. So the moment it comes into the reactor, there is an instantaneous mixing. It becomes equal to the reactor concentration, which is also equal to the effluent concentration. Okay, so perfect mixing, outlet concentration is equal to reactor concentration, steady state operation, constant density, and instantaneous mixing. So these are some of the assumption of a CSTR. Okay, so I hope this is clear to all of you. If you have any doubt, you can ask me, or else we'll move on to the next problem. Right, moving forward. Compared to CSTRs, plug flow reactors are typically dash in their removal efficiency for a given compound. Okay, so here we are comparing a CSTR and a plug flow reactor. Okay, so we have to
B,
tell
B.
me whether
More efficient.
it is more efficient or less efficient. So
More efficient.
more efficient. Okay, any other answer? Someone has also answered it as less efficient, I think. Let me check. Okay. So I'm getting mixed answers. Someone is saying more efficient, someone is taking less efficient. So if you remember, in last class also we discussed a similar type of problem. Okay. So for a given volume, if the volume is constant, here you have to also remember that the volume is also constant for both the reactors. In that case, what should be the correct answer? Just think about it. Others also please try. Uh, Always same people are answering, so I request other people also to try. Okay, so when we are comparing a plug flow reactor and CSTRs, so in a plug flow reactor, the movement of the movement of the reactants are happening in a plug manner, in a plug flow manner. Okay, so by that I mean that there is a continuous reaction that is happening in the lateral direction. So because of which the concentration gradient is higher. Okay, so that's why the PFRs are more efficient than the CSTRs. Okay, and I also told you that a PFR is almost equal to an infinite number of CSTRs. Okay, so infinitely small number of CSTRs is like a PFR. Okay, and also there is a high concentration gradient in the direction of the flow. So that's why the plug flow reactors are always more efficient than the CSTR. So the same explanation also I have given, and also there is no back mixing. Okay, so that's why the reactants are more efficiently uh, degrading, or I would say changing their concentration along the length of the reactor. So always remember the plug flow reactor is always more efficient than a CSTR for a given volume, right? For the same compound, for the same reaction rate, everything keeping the same, it will be more uh, it will be more efficient. We will solve the problem, then we will also see like how it is happening. Okay, how much changes are there. Okay, so we will see in a problem. So for now, you just remember this thing. Next problem. The fundamental mass balance equation relates the rate of accumulation or lessening of a compound to its rate of formation, rate of removal, or both A and B. So here we are talking about the fundamental mass balance equation.
C, both A and B.
Both A and B. Okay. Any other answer? So can someone tell me what is the fundamental mass balance equation? Any idea? What are the parameters?
It was VdC by dt equals to Qn Cn minus Q out C out plus V times 2 rate of formation minus rate of loss.
Yes, yes, that is perfect. Yeah. So that is the fundamental. So that is actually I can say kind of derived from the fundamental. So in fundamental equation, we say that in simpler terms, without using any parameters, we say that the change in change in mass, okay, with respect to time or change in time, whatever you want to say. Just a minute. Okay, so let me denote it as dm by dt. So change in mass with respect to change in time is equal to the rate of input. Okay, rate of input minus some output will be there, minus rate of output. Okay, then there will be some formation might happen in the reactor. So plus rate of formation. Okay, minus rate of removal or degradation. So this is the fundamental equation. So change in mass with respect to time is equal to the rate of input plus minus rate of output plus rate of formation minus rate of removal. So both formation and removal is there. Okay, so that's why option C is the correct answer. Okay. So it is true for any control volume, any type of reactor, everything. The mass balance means it should be the same. So whatever the answer told by you is also correct, but you told uh, in the terms of the constants or the variables. Okay, I told in a more generic manner. So that's what is written also here. Okay, I hope this is clear. Moving forward, nutrient enrichment or eutrophication in water bodies can lead to increased biodiversity and fish populations, harmful algal blooms and oxygen depletion, improved water clarity and recreational value, or none of the above. Okay, any other answer? So, what will happen if there is a nutrient enrichment? Nutrient enrichment, okay, or in bracket, it is also called as eutrophication. So, first of all, is it a good thing or bad thing? Okay, if nutrient enrichment is there, is it good for the water bodies or bad for the water? That is what you have to know. Okay, you might not be aware of the eutrophication term, but if too much of nutrient comes into the water bodies, okay, so what will happen? There will be a high amount of algal cells that would be producing, okay, which we call it as algal blooms. So these are not actually good for the water bodies because they will cover the surface. Okay, they will cover the surface of the lake or pond or any water body, and it will not allow the sunlight to pass through the water body. Okay, and also the oxygen regeneration or the oxygen dissolving capacity of the lake also decreases. So that's why the aquatic life will be suffering, which is inside the lake or pond. So that's why option B is correct. So due to the nutrient enrichment, there will be excess algal blooms which are harmful, and there will be oxygen depletion. Okay. And also these algae produce a produce a lot of toxins, which we call it as algal toxins, which are again harmful to all the aquatic life, animals, mammals, even to humans. Okay, so they will block the sunlight, disrupt the aquatic ecosystem, and harm the submerged plants. So that is what happens in eutrophication, right? So the same thing is written. Let's move forward. What is the primary concern associated with high nitrate levels in drinking water? Algal blooms and taste and odor issues, increased corrosion of water pipes, blue baby syndrome in infants, or all of the above. So, what is the primary concern they are asking of high nitrate level? So, it is a well known disease actually. So, what is the other name of blue baby syndrome? Can someone tell me? Yes, can someone tell me what is the other name of blue baby syndrome? No one knows?
Is it
Yeah, yeah,
methemoglobinemia?
yeah, yeah. That is correct. Okay, that is okay. I will just write it if others don't know, so that there is methemoglobinemia. Yes, this is the correct spelling. Yeah, methemoglobinemia. Right. So this is the major concern of high nitrate levels in the drinking water. And what is the acceptable limit of nitrate in drinking water? Anyone? What is
45?
45? Yes. And also you have to be cautious when we are talking about nitrate levels. Sometimes they are mentioned as nitrate, or sometimes they are mentioned as nitrate nitrogen. Okay, NO3N. Okay, so you have to be very careful. For nitrate, it's 45. For nitrate nitrogen, it is different. Okay, so how much nitrogen is there in the nitrate? For that, the standard is different, and for the total nitrate also standard is different. Okay, so be a little cautious about these things. Okay, so this is the answer. Next, what can you infer from the figure? So we have a figure which uh, depicts the change in the concentration with respect to time. So C by C naught is nothing but it is a ratio of the final concentration to initial concentration. So you can just say change in concentration with respect to time. So we have a PFR line, we have a CSTR line, and the constant of reaction constant is zero point 0.5. Okay, so what do you think is being inferred from the figure? Okay, so since it is a change in concentration, so we can see the concentration in both the cases are decreasing with respect to time. So with more and more time, so at around 10 days, the concentration is zero, around, yeah, approximately equal to zero for the PFR, whereas the ratio for CSTR is little higher, it is zero point 0.2. So we can say 80% degradation is there in CSTR and 100% degradation is there in PFR. So we can directly say that higher rates of removal of contaminant is observed in plug flow reactor. So that's what we have discussed in the first question also, first or second question, that always PFR is more efficient than the CSTR. So that is depicted in the graphical manner. Okay, so you should also know how to read the graphs. Right? Like now moving forward. Okay, so it's a small numerical problem. We have a sewer carrying wastewater containing a compound X enters a nearby stream as shown in the figure below. Concentration of X in wastewater is 250 milligram per liter. The stream has a naturally occurring X concentration of 50 milligram per liter. If the sewer flow rate is 0.5 meter cube per second and the stream flow rate is 2 meter cube per second, what is the concentration of X in the stream after the discharge point? Assume it to be a steady state conservative system. Okay, so steady state conservative system means the concentration is not changing with respect to time, right? It is not changing with respect to time. So you have to find out what will be the concentration of the compound X after the discharge of the wastewater. So at the after just the point of discharging, what will be the concentration? So what concept we have to apply here? Any idea? What is the concept that we have to apply here?
There is the formula like Q and Cn equals to Q out C out.
Yes, so what is that concept?
Is it mass balance?
Yeah, it is mass balance. It is nothing but mass balance. So when you do Q in Cn, so Q is meter cube per second and C is milligram per liter or milligram per meter cube. So meter cube meter will cancel. You will get milligram per second. So milligram per second is nothing but mass by time. So in mass conservation, we always conserve the mass per unit time. Okay. So I will solve it. You will know. Just first of all you just try it out. Then we will see how to solve this. I'll wait for a minute if someone is solving. Is anyone solving or shall I move forward with the answer? And I also request those who have not filled the Excel sheet last time. So please fill that Excel sheet in case I want to share any resources. I'll be able to send you directly through the mail ID. So those who have not filled last time, many people have already filled. You can fill this sheet. Okay. I have put it in the chat box. Okay, coming to the answer. So let's discuss this. So we have a stream that is flowing. Okay. And at a certain point there is a wastewater that is being mixed. Okay, so now the concentration of that X compound in the wastewater is around 250 milligram per liter, which is coming with a discharge of QW as or XW, QW as it is given as 0.5 meter cube per second. Okay, and there is already a stream flowing. Okay, which has a discharge of stream is around 2 meter cube per second, and the concentration of X in that stream is around 50 milligram per liter. Yes. So now at this particular juncture, they both are getting mixed. So what will be the concentration of X after that? They are asking, right? So they are asking. So let us take this as boundary. Okay, so this is first part, this is second part. So in first part, what is the total mass that is coming per unit time? So for any time, if you want to calculate the mass coming per unit time, we generally multiply the discharge with the concentration. Discharge with the concentration. So why we do that? Because discharge is mostly in meter cube per second or whatever. into the concentration. Concentration will be in milligram per liter, or we can write milligram per meter cube. Okay, so these both will cancel and we will get, yeah, 90 is correct. 90 is correct. We will get milligram per second. So we always get mass per unit time. So if we conserve in first first half and second half, our problem will be solved. Okay, so how we have to do it? So in the first half, we see how much mass is coming in. So mass that is coming is Qs into Xs. This is the first mass that is coming in, plus the second mass from the wastewater. So that is QW into XW. So these are the two masses that are coming in the first half. That will be equal to the mass in the second half also. So what is the mass in the second half? So what will be the Q in the second half? Q both will add. So QS plus QW both will add into some X. I don't know that X. So we have to find the X. So what will be my X? X will become Qs into Xs plus Qw into Xw divided by Qs plus Qw. Okay, so this is the general equation we use for mass balance. That's what someone was telling. Q in plus C in divided by Q out plus C out, something like that. So this is the general equation. So if we fill in on the details, we will get Xs is around how much? 2. So 2 into 50. Since all the units are uniform everywhere, so we can just multiply 0.5 into 250, I think. Yeah, 250 divided by 2 plus 0.5. So we'll get around 90 milligram per liter. So after this point, Q will be equal to 2 plus 2.5, that is 2.5 meter cube per second, and X concentration will be equal to 90 milligram per second. Okay. So I hope this is clear to all of you. Like why we are conserving the mass. So in the first half, like in this part and this part, the mass will not change. Why mass will not change? Because there is no degradation. Okay, if we bring degradation into the picture, some bacteria into the picture, or some photolysis, something, then the equations will change because of the degradation. So there the rate of formation, rate of reaction, all this will come into the picture. But here there is no degradation. The mass which is coming in the first half will be carried forward exactly the same in the second half. Okay, and constant, always remember, concentration is not equal to mass. Concentration is milligram per liter or gram per meter cube, something like that. So you cannot simply add 250 plus 50 and write the answer as 300 milligram per liter. Okay, so this is how you have to do it, right? We'll move forward to 90 milligram per liter. Next, okay, it's a little lengthy problem, so we will skip it for now. Okay, if we find time, we will solve this. I will come back to this problem later. I will give the solution, don't worry. Okay, let's solve this. The initial and the final DO after 5 days during a BOD test is given below. Find the BOD in each of the case. So initial DO in first case is 8, final DO is 3. Like that, 4 cases are given. So can submit, this is very simple. Direct calculation is there. So please tell me what
It's
is
like
the,
the initial minus the DO final.
okay, so what will be the BOD
8
in the
minus 3 is 5.
5? What is the correct, what is the BOD in the second case? Can someone tell me?
0.2.
Okay, but okay, now the major thing is, so this is not exactly why I have given this problem, because many of you will think it is simple addition and subtraction, but that is not the case. So in BOD test, there are certain assumption and certain things you have to take care. So in the first case, they are saying that initial DO is 8, final DO is 3. So 8 minus 3, 5. So we report the BOD as 5. That is fine. But whenever the initial DO that is given, whenever the final DO is almost near about initial DO, then we cannot rely on that reading. Okay. So what is happening? So let me discuss it. So if you know the BOD test, we have a BOD bottle like this, okay, and we put our sample, some sample and some aerated water, okay, aerated water we also put with that for dilution or whatever. So so in our sample, the organic matter will be there, right? In our sample, the organic matter will be there. Plus, we are adding some nutrients and also we are adding some microorganisms. So what is happening? And then we are leaving it for 5 days, right? 5 days. So initially we are measuring the DO and then again after 5 days we are measuring the DO. So in these 5 days, these microorganisms are feeding on the organic matter and they are utilizing the dissolved oxygen present. So obviously the dissolved oxygen will come down in 5 days. Okay. So if from 8 it is coming down to 3, so that means some amount of DO has been consumed by the microorganisms and we report the BOD to be 5 milligram per liter, 8 minus 3. But now, if initially it was 8 and it is coming down to 7.8, so that means very less oxygen has been utilized, right? Very less, like zero point 0.2 has been utilized, or it can also be the case that the 7.8 reading I have mistakenly taken it as 7.8, or there is some human error while doing the experiment and the report is coming at 7.8. So we cannot rely on this result. So my DO final should come down by at least 1 milligram per liter. Okay, from 8 it should come down minimum to 7. Okay, then only I can trust that result. Otherwise, I have to repeat it again. Okay, because this can be due to some while doing the experiment some human error, or while measuring the value of DO some error will be there. Okay, so we cannot rely. So that's why for option 2 we cannot rely on that value of our initial and final DO, so we cannot estimate the BOD. Now tell me what about the third one?
The sample has to be diluted more
Sample
to
has
do,
to be diluted more. Why do you think so?
because all the dissolved oxygen is consumed.
Yes,
So
exactly. That is exactly correct. So what happened is in the third case, the DO is moving from 8 to 0. Now we are talking about a 5-day test, right? 5-day test. Okay. So now after 5 days, we are measuring the DO. Now uh, this total reduction of DO could have happened in 1 day, could have happened in 2 day, 3 day, 4 day. We don't know. We don't know the point where it has reduced from 8 to 0. Okay. If we know that point, then we can calculate, right? But we don't know how much time it has taken from to go from 0 to from 8 to 0. So that's why again we cannot rely on this uh, for on this result. Or there can be also case that there is still more organic matter present, but there is no more oxygen that is present in the system. Okay, all the oxygen has been used up. So then also we will not get the correct picture of BOD, because BOD is what? BOD is nothing but an indirect measurement of the organic matter, right? So we measure the organic matter in terms of the oxygen equivalent, or the amount of oxygen that has been used up to degrade that organic matter. Okay, so it's a kind of indirect measurement, not a direct measurement. So again, if it is going to reducing to 0, we cannot rely on this result. Okay. Now again, what about the D? Is it fine?
Same as B.
Same as B. So here also we cannot depend on the final DO reading. It is zero point 0.7. So that means maybe not sufficient DO is present in the microorganisms for their growth, insufficient, because microbes also need some amount of DO, right, to sustain. If it is going to 0.7 milligram per liter, then the microbes are not getting enough oxygen to decompose the organic matter. So again, we cannot rely on the final DO reading. Okay, so except for A part, all the three readings we cannot rely. So that is why. So the same thing I have written here. So I hope you understood. Okay, so though it looks like a simple calculation of BOD test, which is, but there are some assumptions behind it. Okay, so we have to check the final DO reading. So always remember the final DO reading should be less than the initial DO by 1 milligram per liter at least. And also the final DO should be at least 2 milligram per liter so that enough bacteria can survive and decompose the organic matter. Okay, if any of them is not happening, then either we have to dilute that the we have to do more dilution, okay, so that the bacteria falls, so that the DO falls between the range of I would say 2 to 7. Okay, 2 to 7, then it is fine, right? So that is the problem with the BOD test. Okay, so one more thing, like we know that BOD test requires 5 days, right? It requires 5 days to get our result, but we sometimes we don't have that much of time, right? We don't have that much of time. So what is the other test that we can do to get to know about the organics?
CUD.
COD.
COD, right? COD, because COD will give the results very fast, within 2 to 2.5 hours it will give the results. And based on the reading of the COD, suppose for any sewage thing we got the COD as around 100 milligram per liter. So now we generally know that in sewage 60 to 70% is the BOD out of the total COD. So we know, okay, our BOD will be around 60 to 70. So now based on that we will do the dilution and run the test. Okay, so most of the time if we know the characteristics of the BOD of the organic matter like sewage or something else, then we can predict the BOD and then do the test, so that by uh, one trial only we are getting the results. Otherwise we have to do n number of results if we don't know the initial BOD of the system. So many a times when the industrial samples come, we generally don't know how much BOD is there. So even after doing the COD test, we are not able to predict the BOD value at the first trial itself. So that is the problem. Because in industrial samples, it mostly those are chemicals, right? So the COD will be very high, but BOD will be very less. It doesn't always follow the 60 to 70% ratio. Okay. Okay, now I will move forward to the next problem. I think this is very easy. The same problem in CSTR, the concentration in the reactor is same as the concentration of the effluent of the reactor. So that is true. Okay, so I think no need to discuss again. Okay, wastewater sample volume is 4 ml. Dilution water is 296 ml. Initial DO is 7.65. Final DO after 5 days at 20 degrees Celsius is 4.24. The degradation constant is 0.23. So what is the BOD of the wastewater? What is the BOD of the wastewater? Please calculate it quickly and let me know. So in the coming week classes, more and more numericals will be there. So I request everyone to sit with their calculators and with a pen and paper so that we can solve and we'll move forward. So it will be faster. Okay. So quickly just try to answer it. It's a one line problem. So initial DO is given, final DO is given, sample volume is given, and dilution water volume is also given. No one? Okay, let me tell you the answer. So to calculate the BOD here,
Isn't it what like VM times the D initial minus D final per volume of the whole solution?
not
Or
the
let's
whole
say mix.
solution. So what we do, so in last question we just subtracted initial DO, okay, initial DO minus final DO, right? Because there was no dilution given in the question. So now here some dilution is also there. So this is, so I told you, right, in the BOD bottle we will put some sample. Okay, so let's suppose here they are giving it as 4 ml, and the rest of the, so this BOD bottle is always of 300 ml. So the
Yeah.
volume is 300 ml. So the rest of the volume we will fill it with aerated water. So it is around 296 ml. Okay, so when we are diluting the sample like this, we have to multiply with the dilution factor. Okay, dilution factor. So what is this dilution factor? Dilution factor is nothing but the full volume divided by the sample volume. Okay, so nothing, it is nothing but, so what is the initial DO? That is 7.565 minus 4.24 into full volume is 300 divided by 4. Okay, so from 4 we have made up to 300. So around the 75 times dilution we have done. Okay, so this the answer will be 255.75 milligram per liter. This is the answer. Okay, I hope this is clear. So this is only when the dilution is known or dilution is given in the question. If it is not given, then directly subtraction would be done. So these type of numerical problems will come. Next problem, same problem exactly. Now you have to tell me what is the ultimate BOD. So directly, there's a one formula is there. So what will be the ultimate BOD? So what we have found out in the previous problem is the 5-day BOD, right? So now what is the ultimate BOD? What is the formula? What is the formula? So the formula is, so BOD at any time t will be equal to the ultimate BOD into 1 minus e to the power minus k, that is the reaction constant, into the time t. So this is the formula. So BOD t we know 255.75. Ultimate BOD we have to find out 1 minus e to the power minus k. So k given in the question is 0.23 and it's a 5-day test. So into 5. Okay. So if you calculate it, you will get EU BOD as, yes, 374 point around 25, 374.25, something like that. Yeah. So that is correct. Okay, very simple. Next. Okay, match the type of treatment with their primary function. So we have batch reactor, PFR and CSTR. So match the type of treatment with their primary function. Yeah, so again and again we have discussed this. So option B is correct because in a batch reactor there is no mass flow that is coming into or going out. So once all the reactants are put in the reactor, we close it and then perform the reaction. Whereas PFR, they are not mixed along the direction of flow. Okay, so in plug flow manner, like a small CSTRs, it is happening. And in CSTR, there is a mass inflow and outflow from the system. Okay, it's a homogeneous reactor. So option B is correct. Okay, so the depiction is also there. See, so here in batch reactor, it's a closed one. In CSTR, the feed is coming from the top and continuously taken out from the bottom as the product. And in a plug flow, it's a long channel type, like last week we saw that river is also a plug flow reactor kind of thing. So like that, we can visualize that. Okay, so a wastewater stream is mixed with a river nearby. After mixing, formation of certain zones occur. Which of the following zone is characterized by the highest level of treatment of pollutant? Okay, what is the zone of with highest level of treatment?
D. Zone of active decomposition.
Yeah, that is correct. So D, by the name only we can get it. So most decomposition wherever it is happening, so that is the highest level of treatment. So same thing I have shown here. So zone 2, okay, is the zone of active decomposition. The second stage BOD as shown in the figure is due to experimental error, nitrification demand, increased activity of bacteria, interference by certain chemical reactions. So that is very direct question. So obviously the first stage is the carbonaceous BOD. Okay. And in the second stage we have the nitrogenous BOD or the nitrification demand. Because these nitrifiers are like they don't come out easily. They take some time. Okay, so after a particular point of time only, when some of the organic matter or the carbonaceous matter has already been degraded, they they perform and the nitrification demand happens. Okay, so it is also called as stage 2 or second stage BOD. Okay, now some problems. So this is for a batch reactor. So one thing I wanted to ask, do you want me to quickly revise through the mass balance of these different type of reactors, or you know the formula and we can quickly go on with these problems? Or shall I do the mass balance for one or two of the reactors? Revise mass balance? Okay. Okay. So we will revise the mass balance so that it is helpful to all of you. Okay. So I will do it for batch and CSTR for now. PFR is similar to the equation is similar to the PFR so with the batch reactor. So no need of that. So let's see. So let us say for any batch reactor. Okay. So as I told you in a batch reactor, okay, we don't have any inflow, we don't have any outflow. So whatever is happening, we put it in the reactor and then we will close it. So and then some mixing will be happening. Okay. Suppose the concentration inside the reactor is C. Just reactor is C. So as you all know, I have already told you that uh, something like dm by dt is rate of inflow, right, minus rate of outflow, right, plus some rate of formation minus rate of degradation or removal, whatever you want to say. Okay, something like that. So this is the generic equation of for any mass balance. Okay, now dm by dt, we can also write it as, another way of writing is that d of vc into dt. So why vc? So mass I am writing it as volume,
Volume into concentration.
mass per unit time I am writing it as volume into concentration, right? So concentration is also milligram per liter. So volume by time, it will be like more or less same. Since the volume is also constant, we can take this out. We can write v dc by dt. Okay, we can write it as, since the volume is constant for a particular reactor, we can write v dc by dt. Now, what is the rate of inflow that is coming? So generally we put write the rate of inflow as Q in into C in. Okay, that is discharge in into C in. But in the batch reactor it will be zero because there is no Q in. Okay, so we will cancel it later. Then rate of outflow, it will be Q out into C out, right? It will be Q out into C out. Now rate of formation, we can write it as some volume, that is the volume, into the rate of formation minus rate of removal is volume into rate of removal. Now for any batch reactor, my Q in is zero because there is no constant discharge coming in. My Q out is also zero. Okay, the Q out is also zero. And in the reaction, we are trying to degrade it. Okay, so most of the time, there will be some mechanism to degrade the or reduce the concentration of the pollutant or whatever we are trying to do. So there is no rate of formation also. Okay, so all these things will become zero. Only the rate of removal will be there. Okay, so now we can write V dc by dt is equal to minus of V into some RR, rate of removal. Okay, so this V and V will cancel again. So we will get it as dc by dt is equal to minus RR. Now we have
Kc.
to, sorry,
Yeah, I said the rate of loss is Kc. Rate
Kc.
of constant times to the concentration of compound.
Yes, but why it is only Kc? Why not Kc to the power 2 or Kc to the power of 0?
Because it's in first order
Yes,
reaction.
yes. So now for most of the cases, we will assume it to be a first order reaction or first order degradation. So that's why it is minus Kc. Okay, it can be power of 0, it can be power of 2, power of 3, whatever. But we are assuming it to be a first order reaction. So it is Kc. Okay, so now we will just have to mathematical solve it. So dc by c is equal to minus kt k dt. Okay, we will integrate both the side, and after integration we will get something of like this. So c at any point of t will be equal to c naught into e power minus k. Okay, so this is the final equation we will get. Okay, so C we will integrate it from C naught to Ct, and the time we will integrate to 0 to t. So once we do the integration, we will get Ct is equal to C naught e to the power minus kt. So mathematics I am not going into because it is well known. So this is the basic equation of a first order reaction in batch mode. In batch mode. Okay, so this same equation will be used for everything. Okay, so based on this equation only we will develop. Now what happens for a CSTR? So what happens in the CSTR? Same thing. Again, one reactor is there. There is some inflow is coming. and there is some outflow that is going out. So let's say the inflow is coming with a discharge of Q in with a concentration of C in. Okay. Outflow is going out as a concentration of Q out, as a discharge of Q out and concentration of C out. Okay. And inside continuous mixing is also happening. Okay. And inside also some concentration will be there C, and we know that C is equal to always C out, because whatever the inside concentration will be there, it will be equal to C out. So this is the basic assumption or the flow diagram of a CSTR. Now again same equation we will put. So what was the equation? That was V dC by dt. Okay, it is equal to Q in by C in minus Q out C out plus some V of rate of formation Rs minus rate of removal Rr. Okay, so this is the equation. Now for any CSTR, when a constant inflow and outflow is happening, we also assume one more thing, that we assume it to be at steady state. Okay, so I told you at steady state concentration, as steady state condition, my dC by dt will be equal to 0. Okay, with respect to time, there will be no change in the concentration. Okay, there will be no change in concentration. So what will happen? This dC by dt will become 0. And another thing is Q in and Q out. Okay, so dC by dt is equal to 0. And also we assume that the Q in that is coming in, Q out that is going out is equal and equal to Q. That is same. That whatever discharge is coming in, the same is going out. So Q in and Q out is same equal to Q. It is equal to Q. So now after simplifying, it becomes 0 is equal to Q into taking common C in minus C out plus V into, now RF rate of formation I am taking at 0 because nothing is getting formed. So 0 minus RR. Okay, RR again it will be K into C naught. Okay, or C naught or C in. I will write just C. I will write, sorry, C. It will be KC. Is it okay? Any doubt in this? Okay, so on simplifying, this will be equal to some, like I am writing it as C naught, C in as C naught, C out as C. Okay, and if you just solve it, you will get something like V by Q is equal to C naught minus C by KC. Okay, so this V by Q is nothing but the hydraulic retention time. Hydraulic retention time, we will denote it as theta. So this is again one more uh, equation for CSTR for first order. Okay, so just to give a revision of batch reactor and the continuous stir type reactor. I hope this is clear. Any doubt in this? Okay, we will move and solve the problem now. So here it says that batch reactor, in a batch reactor, an experiment is run in the lab to remove propionic acid. So propionic acid is our contaminant. It is a common organic acid that is used in the production of various chemicals, and it is often present in industrial waste stream. So this is the generic information. Now initial concentration is 21 milligram per liter. Concentration after 30 minutes is 3.5 milligram per liter. Assume that propionic acid can be removed by a process which can be described by first order reaction. Okay, that is R is equal to Kc. Assume steady state. So for this given information, estimate the rate of reaction. So they are asking what is the rate of reaction. So I have just now derived it. Please put in the values and tell me the final answer. I'll wait for a minute. Anyone with the answer? Anyone with the answer? I hope you know the formula. This was the formula.
Yeah, it's like Ct equals to C naught times the e to the
Okay.
power
What is the
minus
answer?
k
What is
times
the
the t.
what is the k value?
So k, we should take like ln of c by c naught equals to minus k times the t. So I know the c and c naught, I know the t. Well, I guess we have to change the time from unit minute to second, then we can derive the k.
Yes, yes. Tell me what is the answer you are getting.
Okay, I haven't calculated till now.
Okay. Okay, so simple thing. So C is equal to C naught e to the power minus kt. So 3.5 is equal to 21 into e to the power minus k into what is the t? That is 30 minutes. Okay. So if I am keeping it as 30 minutes, the answer will be I will be getting will be in per minute. So the k I will get as 0.0597 per minute, because the unit of k is per minute, per time, so per minute. And if I change into seconds, it will be 3.5 as per second. Okay, so in this type of problems you have to always be careful, like in what unit they are asking. So they are asking the answer in per second. So even if you find the correct answer in per minute, if you put in that particular value, your whole solution will be wrong. Okay, so you have to see the particular unit and answer it accordingly. So here they are asking in per second. Okay, so that is the answer. Next. Next is, so same question. So the bold part is the same. So they are asking, if the treatment system is plug flow, calculate the hydraulic retention time which would be required to achieve an effluent concentration of 1.5 milligram per liter with the same initial concentration in the experiment. Okay, so they are saying that now initial concentration is same, the final concentration is 1.5 milligram per liter, and the reaction rate is same, that whatever we calculated in the last question. So now what will be my hydraulic retention time? So one thing I just want to tell you, the formula for PFR and batch reactor is the same. Okay, they have the same formula. So instead of T, it becomes theta. Theta is the hydraulic retention time. So now can someone tell me what is the theta or the T for hydraulic retention time for the plug flow? The formula is the same. I think no one is solving these problems. Please, I request, maybe today you don't have the calculators, but from next time, please try to bring the calculators and solve it within the class, so that you will get the practice and it will help you in the exams. Because though you will be knowing the formula, everything, in the exam, the problem will happen. So for the PFR also it is the same. So instead of T, I am writing it as theta. The formula remains the same. So final concentration is 1.5, initial concentration is 21 into e power minus k K is 0.0597, which whatever we calculated in the last question, into the theta. So if you solve this, you will get theta in minutes directly because I am using the K value in per minute. So theta will be in minute, that is 44.20 minutes. Because they are asking it in minutes, the theta to be in minutes. Okay, here you can see, right? So the same thing. Next, similar problem again. Now they are asking that if the treatment is completely mixed flow reactor, calculate the effluent concentration if the hydraulic retention time is 50 minutes. Okay, so now they have changed the hydraulic retention time to 50 minutes and the K is same. Now we have to find out what is the effluent concentration. So here again, so for CSTR, the equation as we derived is C is equal to C naught by 1 plus K theta. Okay, so instead of V by Q, I am directly writing it as theta. So this is the equation for the CSTR. So here it will be, so C we don't know. C naught is 21, 1 plus 0.0597 into theta is 50 minutes. So I will get theta C as 5.27 milligram per liter. So you can simply see, if you compare these two answers, you can see that in CSTR, okay, it is taking 50 minutes to come to a concentration of 5.27, right? Whereas in PFR, for the same reaction rate, it is taking only 44.2 minutes to come to a concentration of 1.5. Okay, so that is why PFR is always more efficient than CSTR. Okay, so here initial concentration is same, the reaction rate is same. So CSTR is taking more time to come to a higher concentration than PFR, which is taking less time and coming to a lower concentration. Okay, so I think now it is much more understood. Okay, the same question, the flowing liver is an example of, very simple, it's a plug flow reactor. So I think everyone knows that. So not a big challenge. Okay, next problem. Which of the following represent the correct reagent for COD test? So we have the COD test. So which of the set of reagent is correct? So please tell me. B. Okay. Any other answer? C. Okay. Any other answer? C.
It's B. Potassium chromate, sulfuric acid, silver nitrate, and mercury sulfate.
Okay.
So C. C is the right answer.
C.
C. Okay. The first question is whether it is potassium chromate or potassium dichromate. So the simple thing to be remembered, we have to use a very strong oxidizing agent, because what in COD test what it does is it will we will add a very strong oxidizing agent and it will reduce itself and oxidize the organic matter completely, right? So that is why, and it has to happen in the presence of an acid. Okay, so sulfuric acid will definitely be there, which is there in all the options. And the strong oxidizing agent is potassium dichromate. So that's why potassium dichromate is very much important in any COD test. So potassium dichromate and sulfuric acid are the primary reagents for a COD test. Now what happens? Now what happens is, if you see the formula, in the first formula you can say dichromate, that is Cr2O7, it get reduced. because it is oxidizing, so it will get reduced to Cr3 plus, and that H plus, that 14H plus is nothing but the H2SO4. And this reaction is catalyzed uh, by the help of silver sulfate, that is AgSO4. So silver sulfate is also important in the reaction. Now the problem with this COD test is if chlorides are also present in the system, so that also interferes in the reaction, because that chloride itself, if you see the second formula, that 6Cl minus will also use up some dichromate to oxidize itself. Okay, so that's why to remove that chloride interference, we have to add the mercuric sulfate, that is HgSO4. Okay, so that's why that if you see the third reaction there, you can see Hg2 plus will react with the chloride and it will form HgCl2. Okay, so that's why all the first four reagents marked in option A are required in any COD test. So potassium dichromate as a strong oxidizing agent, sulfuric acid to make the system acidic, silver sulfate as a catalyst for the reaction, and then mercuric sulfate to remove the interference of the chloride. Okay, I hope this is clear. So you will not generally see this silver sulfate or mercury chloride being added separately. It is added with the sulfuric acid itself. Okay, so that's why we don't add sulfuric acid, we add COD acid. So we have to prepare COD acid separately. So in that COD acid, we will add these two things. I hope this is clear to all of you. Okay. So this was about the COD test. Next. Steady flow is no change in velocity with distance, velocity changes with time, no change in flow rate with time in a stretch, or flow rate changes with time. So what do you mean by steady flow?
D. D is the right answer.
D.
D.
No
No,
change in velocity with distance. A.
no. So whenever we say steady, steady means there should be no change. Now that can be no change in velocity also. There can be no change in flow rate also. Both of the thing can be.
C. Flow.
Yeah, but whenever we say steady flow, we generally mean with respect to time. Okay, we generally mean with respect to time, it is not changing. That's why most of the time we will write dc by dt equal to 0. We will not write dc by dx equal to 0. Okay, so dc by dt. So that's why option C is correct. Okay, so no change in flow rate with respect to time in a stretch. So C is the correct answer. So steady flow refers to a situation where the hydraulic properties, be it flow or velocity or depth of the channel, do not change with respect to time. And there is another thing, uniform flow. So uniform flow we define with respect to distance or space. Okay, steady flow with respect to time, uniform flow with respect to space or distance. Next, when sewage enters the river, the rapid depletion of dissolved oxygen is due to change in temperature, the suspended particles, respiratory activity of aquatic plants, or microbial activity. So why there is a rapid depletion? So this is very easy, microbial activity, because the sewage, when it enters into a river, it carries a lot of organic matter. So the moment the organic matter is put into the river, so the microbes present in the river will act upon the organic matter to degrade it, and in that way they will deplete a lot of dissolved oxygen. Okay, so D, microbial activity, is the correct answer. Okay, so this question regarding Pecklet number. So which of the following represents the correct information regarding a Pecklet number? So Peclet number you might have heard in the classes. Uh, so I think the options are marked incorrectly. It should be A, B, C, and D, not all A. So let me know what is the correct option. So we are comparing the Peclet number of a PFR and a CSTR. So what is the Peclet? So what is the correct answer here? Any idea? So if you know the formula, half of the problem is solved.
So this is
A.
the
A. Yeah, A is the correct answer. So for others, let me just clarify you. So Peclet number is nothing but the ratio of advective flux by dispersive flux. So this is the definition of Peclet number. Now how we denote it? We will denote it as QL by AD. Okay, so Q by A, discharge by area is nothing but velocity or U. Okay, so UL by D, UL by D. So these things will refer to advection. So advection in last class I told you it is a bulk movement of the fluid. Okay, so with the fluid the transport happens. And D is the dispersion. D denotes the dispersion coefficient. Okay, so advection by dispersion flux is the ratio of the Peclet number. So now just imagine for a PFR which is very long, okay, very long, there will be a major advective flux that will be happening throughout. Okay, so advective flux will be higher because the stretch is very long, some length will be there. So that's why the numerator will increase. The numerator of the Peclet number due to advection in a PFR will always increase more and more. So and somehow it will tend to infinity. So that's why the Peclet number of a perfectly performing PFR will be infinity, whereas in CSTR the dispersion will be more than the uh, advective flux. Okay, so just remember it that way. So Peclet number will be infinity for PFR and zero for the CSTR. Okay, so this is another diagram. So no need to get into all this. Just remember advection by dispersion. So since it is a longer channel, advection will be more in the PFR. So that's why it may tend to infinity, whereas in CSTR the reverse will happen. Okay. So again, similar kind of problem where initial concentration, final concentration is given, flow rate is given, and reaction constants are given. So I'm not going to solve this, but I will give you the solution, give you the answer for this. Okay, so just take a screenshot of it, try it out by yourself. If you have any problem in getting these answers, you can write a mail to me. Okay, you can write a mail to me. I will give you the solution in case. But I think it is these are very simple problems. You'll be able to do it. So I will skip the question for now, and we can solve some better problems. Okay, because already we have seen many objective type of problems. Now we will solve some subjective type of problems so that it will give the concept better conceptual clarity. Okay, so this is one question that we are going to solve now. So suppose there are three CSTRs in series, okay, with the second reactor being twice the size of the first and the third reactor. Okay, I will explain it. Now the pollutant concentration that is coming in the first reactor is 150 milligram per liter with a flow rate of 400 liters per minute. The reaction rate constant is 0.007 per hour, and the rate only depends on the pollutant. Now we have to calculate the removal efficiency of the reactor along with their HRT for a overall 80% removal. Okay, I think uh, this question looks a little bigger, but it is very simple. Okay, we will solve it in step by step. So in that way, we will be solving many objective type of problems. So let's see. I will explain this question once again. Okay, so let's start. So what this question is saying is, you can take a screenshot for your reference. Just I am opening it again. Yeah, just take a screenshot of this problem so that you can refer to this problem. Okay, right? I think you have done it. Okay, so 25. So they are saying that we have three CSTRs, 1, 2, and 3. And they are saying that the second CSTR is twice the size of the first and third. Okay, so this is 1, this is 2, this is 3. So now some influent is coming like this, and these are in series. Now the effluent of this reactor is now coming as an influent of this. Then again the effluent of this reactor is coming as an influent of this. And then some effluent is coming out from here. Okay, so this is the basic sketch of the problem. Now they are saying that suppose the initial concentration that is coming C naught is 150 milligram per liter. Okay, and the discharge Q is around 400 liter per minute. 400 liter per minute. And the same Q will be followed everywhere. Okay, there will be no change in Q. The same Q will be going through in each of the reactors. And the reaction rate constant is 0.007 per hour. Okay, and the overall efficiency is 80%. So what do you mean by that? So suppose the initial concentration is 150. Okay, the final concentration, okay, that is coming from the third reactor will be 20% of 150, because 80% is getting degraded, so it will be 30 milligram per liter. So from here it is entering it as 150 milligram per liter. Whatever is coming out from here, that is C3 will be equal to 30 milligram per liter. So now we have to find out what will be this C1 coming out from here and what will be this C2 coming out from here, because this same C1 will be coming here and this same C2 will be coming here. Okay, is the question clear to all of you? Is anyone is having any doubt regarding the question? Please tell me. Can someone confirm if they have understood or any doubt? Shall I move ahead?
Yes, please.
Okay, okay. And the other information that is given is the V1 volume 1 is equal to volume 3. Okay, and volume 2 is twice of volume 1 or twice of volume 3. Okay, so this is another information that is given. So now let's solve the problem. So let's focus on the first reactor. So in the first reactor, what is happening? 150 milligram per liter is coming in. Okay, and some C1 is coming out of it. So what is the basic equation of a CSTR? So basic equation of a CSTR is C equal to C naught by 1 plus kV by Q. Okay, 1 plus kV by Q. So instead of theta, I am writing it as kV by Q. So what will happen? So here C is nothing but C1 and C naught is 150 milligram per liter. Okay, or else just leave it like that. For now, just leave it like that. We will not put in the values right away. So we will write just C1. Okay, C1, that is the final concentration, will be equal to C naught by 1 plus kV by Q. Or we can write C1 by C naught is equal to 1 by 1 plus kV by Q. So this is my first equation. Now what is happening in the second reactor? In the second reactor, the same C1 is coming and whatever is coming out is C2. So if you write the reaction again for this, it will be similar as C2 by C1 will be equal to 1 by 1 plus K Now here it won't be V, it will be 2V because it is twice the size of the first reactor. So 2V by Q. So this is my second equation. Now what will be my third equation? Third equation will be same, C2 will be coming in and whatever is going out is C3. Okay, so it will be C2 or rather C3 by C2 will be equal to 1 plus 1 plus kV by Q. So this is 3. This is my equation 3. Okay, so these are all my equations. Now what I will do, I will multiply equation 1 into equation 2 into equation 3. Okay, so what will happen? First I will multiply the left hand side. It will be C1 by C0 into C2 by C1 into C3 by C2. Okay, this will be equal to 1 by 1 plus kV by Q the whole square, because two terms like this will come, and 1 plus K 2V by Q. One equation will come like this. Okay, so now if you see this equation, C1 will cancel, C2 will cancel. We will only get C3 by C0 equal to 1 by 1 plus kV by Q square plus 1 plus kV K2V by Q. So now we know all these things. C3 we have calculated 30 by 150. 1 by 1 plus K is 0.007. Now volume we don't know, that we are going to find out into volume divided by Q. Q is given as 400 liter per minute. Okay, or since our reaction rate constant is given in hour, so we will convert into an hour. So it will be 24,000 per hour ka whole square plus 1 plus K 0.002 into 2V by 24,000. Okay, so if you solve all this, we will get V as 1871962.61 liter, or you can write as 171871.96 meter cube. So this is V. So this is V means V1 equal to V3 equal to V is equal to 1871.96 meter cube, and my V2 equal to 2V will be equal to 2 into 1871.96 meter cube. Right? So till now I think everything is clear. So once we get these things, now we can calculate C3 and C2, because if we put the parameters now in this equation, so only C1 is unknown, C0 we know, K, V, Q, everything we know. So simply we will put, so from now equation 1, we have C1 by C0 is equal to 1 plus 1 by 1 plus KV by Q. So this is C1 we don't know, C0 is 150 by, okay, so 1000. So C1 we will get it as 97 milligram per liter. Okay, C1 we will get it as, and what is the efficiency of first reactor? First reactor efficiency is 1 minus 97 by 150. Okay, so it will be around 33.55.33%. Now similarly from equation 2, okay, you will get C2, I am just directly writing 46 milligram per liter, and efficiency of 2 will be 52.577%. Same, directly formula we have to put, and from equation 3 you will get as C3 we already know, so this is 30 milligram per liter. So for efficiency of third reactor will be again 35.33%. Okay, so is this clear? I hope. Any doubts in this problem? Anything that you didn't understand? It looks a little complex problem, but direct formula application is there. Okay, just I am showing it once again how we have solved. So first individually one reactor you take, make the three equations, then multiply all the three equations, it will simplify and you will get the volume. Once you get the volume, okay, put back the volume in the individual equations to get the concentration. So now in exam, any like lot many information will be given and any of these part can be asked. So that's why if you solve one problem like this, it will be helpful to solve all the other problems. Okay. So the answer. Okay. Next problem. It says that a 24 meter cube reactor operating in plug flow mode reduces BOD in wastewater from a value of 250 milligram per liter to 10 milligram per liter in detention time of 10 hours. So if the rate constant is 0.23 per day, find the order of reaction. So here they are asking to find the order of reaction. Till now we were seeing like how to find the reaction concentration or the effluent concentration or the reaction rate or time. But now they are asking the order of the reaction. So for this uh, you have to be knowing the formula for each of the order of the reaction, because whatever formula we have derived in previous question, it is only for first order reaction. Okay, so since it's a plug flow reactor, I will give you the equation of all the order of the reaction. Okay, so let me write it down. So for any PFR, okay, if the order of reaction is 0, then my effluent concentration will be equal to influent concentration minus K into the HRT. Okay, for order 1, we all know CE is equal to C naught e to the power minus K into HRT. For order 2, it is C is equal to, or it is not in this form, it is 1 by CE is equal to 1 by C naught plus K into HRT. So I am not deriving all these things, but I am rather giving you the equations directly. So in the question, we know C naught, we know K, we know HRT. Just put it, okay, and see whether you are getting the effluent concentration. So in whichever order you are getting the effluent concentration as per the calculated concentration, that will be your order of reaction. Okay, if you solve this, you will get in the second order reaction for the particular problem. So my order of a reaction will be 2. Because for the other things, so suppose for the first order reaction, initial concentration is 250 minus 2.0.23 into 10. So you will get something around 240 something. Okay, but the effluent concentration is 10. So it is not matching. So it is not first zero order reaction. Similarly, if you put the values here, you will get something around 227.15 milligram per liter. So this is also not the effluent concentration which is given as 10. But whereas if you solve this, you will get the answer as 10.01 milligram per liter. So this is correct. So the order of the reaction is 2. So like that you have to solve. Okay. Okay. So yeah, these were the questions which I wanted to discuss for today's class. I hope you have understood everything. And in case you have any queries, you can contact me directly at saha19akash@gmail.com. Okay, and the next session will be on Tuesday, 7 to 9 p.m. That is on 10th February. So we will be discussing on that day about the contents of week 3. Okay, so today we discussed about week 2. So next class we will be discussing about week 3. So I hope you are enjoying the class and
Sir, I think this mail is bound.
sorry.
I have mailed to bound this.
Oh,
I
you
have
have mailed
mailed.
me.
Yeah, your email ID is bounced.
Okay, okay, I will check the mail. Okay, I will check the mail. Uh, because I was not well for the past few days, so I couldn't
Yeah.
check the email. Okay, I will
Sir,
check.
you have told me you have provided the PDF of this, but we have not received any PDF.
No, so these PowerPoint are already being uploaded. Okay, you will get the link from the NPTEL team. Okay, so all the PDFs and whatever we are discussing, this recording is also being uploaded in YouTube. Okay, so even if you miss the class, the next day I will just write my YouTube channel name, Akash Saha NPTEL. Okay, Akash Saha NPTEL. If you go to this channel, these lectures will be uploaded in case you miss the class. Okay, so all the materials will be provided to you. Don't worry about it. And in case some extra material that I have to provide, I will directly provide you through the email. And this email ID, you can connect with me in case you have any query with the assignment problems or any other in general uh, topic related problems. You can ask me. I will be happy to help.
Okay, sir. Thank you.
Okay, thank you. Any other doubt? Anything you want me to improve or you want me to add? Please let me know. Or if you are happy with the classes, I will go as such. Okay, that's all from my side today. In case you don't have any more doubts, you can leave the session. Thank you so much.
Thank you, sir.
Thank you. If you have any doubts, you can ask me now also.